Root 3 presentation.
This diagram shows the system architecture. The client communicates through name service to find the required service. Requests are processed across distributed nodes. Shared data acts as the shared storage, and data is replicated across node A, B, and C to ensure consistency. This demonstrates communication, replication, and consistency in a distributed system.
Next, now I will talk about diagrams. Here, there are two diagrams that simulate thread-based and process-based, which is the first diagram, has shown that there are shared memory. The achievement is to call one 3000 value, whereas all 5 threads can access it, which is writer 1, 2, and 3, and reader and monitor. And the second diagram is process-based, which is 3 process in the separate, meaning that each process does the counter independently without affecting another threads. Both writer A, B, and C counter 0 to 1000.
Assalamualaikum, my name is FAHIM. Now, I will continue with my section naming system architecture. First, flat naming. Flat naming uses a simple identifier like experiment.id pointing to a value. The implementation is Java concurrent hash map. The lookup operation is big O of 1, meaning constant time regardless of data size. In our performance test, flat naming achieved 0.0020 millisecond per lookup. That's extremely fast. However, the limitation is flat naming provides no structure. You cannot do wildcard queries or search by properties. Next is structured naming, which work like domain name system. The format used separator paths. For example, db.primary.shop.com points to 10.0.0.1. The powerful feature here is wildcard queries, with one query like star.shop.com. You can find all services under the shop.com domain. In our test, this return 3 services. For exact mesh lookups, it takes 0.05 millisecond. For wildcard queries, it takes about 2.3 millisecond. This is acceptable because wildcard queries are less frequent. The third scheme is attribute-based naming. Instead of knowing the exact name, you can find a service by what it is. For example, a payment service with tag like region equal Asia and role equal primary. You can then query using search by tag to find all services in the Asia region. In our test, it's written one service. The trade-off is performance. Attribute-based naming is the slowest at 0.1 millisecond per lookup. That's 50 times slower than flat naming. But this is acceptable because discovery queries are less frequent. Now, let me compare all 3 naming schemes side by side. As shown in the table, flat naming is the fastest with 0.0020 millisecond latency and big O of 1 complexity, but it has no wildcard or property search support. Structured naming offers wildcard queries like star.shop.com at 0.05 millisecond for exact mesh and 2.3 millisecond for wildcards. Attribute naming is the most flexible with property search like region equal Asia, but it is the slowest at 0.1 millisecond, which is 50 times slower than flat naming. In terms of speed, flat naming is the fastest than structures than attributes. In terms of flexibility, attribute is most flexible than structures than flat. Based on our plots, 80% of requests use flat naming, 15% use structured, and 5% use attribute. This gives us a weighted average latency of only 0.0085 millisecond. Our cache achieved a 75% hit rate with only 20 kilobytes of memory. All 6 units test pass confirming our naming service worked correctly.
My name is NAZMI and I will be presenting replication and consistency. So basically for this project, we are implementing a multi-node active replication design. As you can see, we are having 3 nodes, which is node A, node B, and node C. And for the sequential consistency implementation, so we are relies on this reentrant lock object. So basically when the simulation run with locking enabled, so the mechanism enforce a strict mutual exclusion boundaries. So at the same time, it will ensure that every replica transition to the exact same execution sequence without any data conflicts. So for eventual consistency implementation, which is activated when use lock is set to false. So in this mode, basically the synchronization barriers are completely dropped to allow multiple thread workers to modify the cluster node concurrently. So next we have increment method. So this is where our cluster states change are executed. So this for loop dynamically push the new updates to all available cluster nodes to simulate active propagation. So when the sequential consistency is enabled, the process hit this lock.lot boundary. So this is to guarantee that all replica transformation occur automatically and in a globally synchronized sequence. However, in a eventual consistency mode, the lock is bypassed and this thread.yield direct is triggered. So this basically explicit forces a CPU context switch mid transaction to simulate a real world propagation delay and network jitter. So our architecture is can be said successfully demonstrate structural race condition and data drift across the cluster. But not least, we have safe state and cluster reset. So for this part, we are safely verify and clear out our cluster states. So basically we have the get counter and reset methods. So both data retrieval and maintenance tasks are wrapped inside the identical log monitoring blocks. So basically when the synchronization is active, these boundaries completely eliminate dirty or stale reads. So this guarantee that any query request targeting a specific replica node will always return a perfectly uniform and aligned value across the system timelines.
First, we compare thread-based and process-based execution. Threads share the same memory space, allowing faster communication and lower resources consumptions. Processes provide better fault isolation, but they require inter-process communication and consume more resources. Therefore, threads were more suitable for our system because our workload involves frequent access to shared data. Next, we analyze three naming approaches: flat naming, structured naming, and attribute-based naming. So we adopted a hybrid naming strategy that combines all three. Finally, we compare the sequential consistency and eventual consistency. Sequential consistency guarantees correctness but introduces higher latency. Eventual consistency improves speed and availability but may temporarily return stale data. These trade-offs become one of the most important findings of our project. To evaluate our design decisions, we conducted several experiments. The race condition experiment produces the most significant result. With the synchronization enabled, the system completed all 3,000 updates successfully with no lost data. However, when the synchronization was disabled, the executions become approximately 5.5 times faster, but 1,334 updates were lost due to concurrent access conflicts. This clearly demonstrates the trade-offs between performance and correctness. For naming performance, flat naming achieved the fastest lookup time at only 0.002 millisecond. Structured naming required approximately 0.05 millisecond, while attribute-based naming required around 0.1 millisecond. Although attribute-based naming is slower, it provides greater flexibility for dynamic service discovery. We also evaluate caching performance using the LRU cache. The system achieved a 75% cache hit rate and reduced lookup latency by 58% while using only a small amount of memory. During the node failure testing, sequential consistency became unavailable because it waited for all replicas to respond. In contrast, eventual consistency maintained 100% availability, although some stale reads occurred temporarily. This experiment demonstrates the CAP theorem in practice.
The project follows a modular design where each class has a specific role. Clear naming and consistent coding style improve readability. Comments are used for important section. The system also uses synchronization, logs, and countdown latch to manage thread and ensure data consistency while reducing race conditions.
Based on our finding, we recommend a hybrid architecture consisting of thread-based concurrency, a combination of flat structured and attribute-based naming, LRU caching for frequently accessed resources, and configurable consistency where eventual consistency is used by default and sequential consistency is reversed for critical operation. The most important lesson learned is that distributed systems are not about choosing the faster or the most consistent solution. Instead, they are about selecting the right balance between performance, consistency, availability, and scalability according to the application's requirements. Thank you.